logarithmic functions, an exponential, just to kind of review this, an exponential function passes, all exponential functions pass the point 0, 1, okay? And if they're exponents, the variable is the exponent. So as x gets negative, a negative exponent means you're taking the reciprocal, and when you take the reciprocal of very large numbers, they get very close to 0, okay? And on the other side of the coin, you've heard of the term exponential function or exponential growth. It increases very rapidly, so it's going to look something like that, okay? That's an exponential function. And then the partner with the exponential function is the logarithmic function. So if you take every single point on this graph, this exponential function here, and interchange x and y, that will produce a logarithmic function. So here we have 0, 1, which every exponential function passes through 0, 1. Well, every logarithmic function passes through 1, 0, because you switch x and y. So this point down here is 1, 0. And then it's the mirror image of this function, of the exponential function, across the line y equal x. Okay, I don't know if you remember talking about this. Okay, so the form that we have, and first for section 2.2, we are going to be looking at finding the derivative for the function y equal e to the x. This is a particular kind of exponential function with base e, and e is a constant which is approximately equal to 2.7, okay? It never changes. It's always the same value. It's an irrational constant. That's why we use a letter to name it, because to really talk about that constant would be, you know, you're not going to write 2.7 because it's not equal to 2.7. It's about 2.7. You know, that's just the approximation. So we talk about the constant e. It has a special importance in natural sciences, but I don't want to get into that right now. So the point is, this is a constant. The variable is the exponent, and that's why we call it an exponential function. So the derivative rule that we're going to learn today for the derivative of y equals e to the x is y prime equals e to the x, okay? It just so happens that the derivative is exactly the same function. I think that's a real curious thing, but anyway, it is. So, so every tangent line that you draw, if you calculate the slope, the behavior of that slope is identical to the function itself, okay? So let's do some examples. All right, just like all the normal derivative rules apply to this function, just like any other. So for example, if you have a constant multiple, 2e to the x, then the derivative is, the derivative of the constant multiple is the constant multiple of the derivative. So we just have y prime equals 2e to the x. And since the derivatives is the same as the original function, nothing changes. Now, what if your constant is in your exponent? Well, now 2 to the x is a different function. It's not just plain old x. So we're going to have to use the chain rule, because instead of x being your input like it is here, now we have a function of x that is the input. So the chain rule applies. So the derivative, when you're taking the derivative of an exponential function, you're just going to copy what you see there, okay? Because it's the identical function, right? So I'm just copying what I see. But then because this is not just plain old x, I have to multiply by the derivative of this inside function, and the derivative of 2x is 2. So this just becomes y prime is equal to 2e to the 2x. Okay? So in general, if you have a function y equal e to the some constant kx, then your derivative is going to be k e to the kx. All right? That's just an aside there. Any questions so far? All righty. Let's suppose we have a function x to the 7 minus 5e to the 2x. I like this problem because it gives me an opportunity to point out something to students that's very important, that is often overlooked. Both of these functions here that are subtracted have exponents, right? So you might think that they're both exponential functions because they both have exponents, but it's not that, okay? This is a power function. Yes, it has an exponent, but the difference here is the exponent is a constant and the base is the variable. Whereas here, for this exponential function, the base is constant and the exponent is a variable. So that's what defines an exponential function, is you have a constant base with a variable exponent. So let's take the derivative here. This is a power function, so we're going to apply the power rule. This is an exponential function, so we're just going to copy what we see there. And then, because this is not just plain old x, I'm going to multiply by the derivative of this inside, and that's 2. So simplifying, I get f prime of x equals 7x to the 6 minus 10 e to the 2x. Okay, think about that for a minute. Any questions or comments that anybody wants to make? Okay, example 4, and I'm just kind of increasing the complexity here of each example, hopefully in a manner that is easy for you to follow. So now we have a function y equals e to the 2x divided by x to the 10th power. All right. Again, you can see we have a power function in the denominator and an exponential function in the numerator, but we're taking the quotient. We have a quotient here, so we're going to use the quotient rule. And if you will recall, if you have two functions that are divided like this, the derivative is the bottom function times the derivative of the top minus the top function times the derivative of the bottom divided by the bottom function squared. This is the quotient rule. And because I have a quotient here, I'm going to apply this rule. So the bottom function times the derivative of this, remember we showed that that was 2e to the 2x, minus the top function, which is e to the 2x, times the derivative of this power function, which is 10x to the 9th, all divided by x to the 10th squared. All righty, now I'm going to simplify, and we have 2x to the 10 e to the 2x minus 10x to the 9th e to the 2x. when you take a power and raise it to another power, you multiply the exponents. So this is x to the 20th power. And you'll notice that I have some powers of x in the numerator and the denominator, so I think some of those will cancel. So let me go ahead and factor out x to the 9th. And then I'm dividing by x to the 20th. And when I factor out that x to the 9th, I'm left with 2e to the 2x minus 10e to the 2x. Okay, and I could go ahead and take out, oh wait, I missed something here. When I took out this x to the 9th, there's an x in there because this is x to the 10th, so I have an extra x. Okay, now you can see I can simplify this here because I have 9 copies of x in the numerator and 20 in the denominator, so this is going to simplify as the numerator. I think I'll, let's see, 2e to the 2x minus 10e to the 2x over x to the 11th. Okay. I think that's good enough. We'll just leave it like that. You could factor out e to the 2x, but you can't really cancel it with anything, so you might as well just leave it in there. Okay.